We definitely confirm that the lander is on the surface, and I leave it to Stefan. I think it's up to him to judge how it's going now on the lander.
The landing gear has been moved inside, so we are sitting on the surface. Philae is talking to us, more data to come and to be analyzed right now.
We take an image that just arrived here, so it's really not processed, it's really as it is.
So we have the first images taken by the orbiter, by Osiris.
The lander may have lifted off again. We touch down, and we're rebouncing. We still got radio link, we still get science data from there. So maybe today we didn't just land once, we even landed twice.
Ladies and gentlemen, welcome back to ESA, the European Space Operations Center here in Darmstadt. And you see, yesterday was great, but today will be even bigger. Ladies and gentlemen, we have images over the night, and we are running a little bit late because they have to be processed, and that was, the scientists were busy at the last hours, and here we are. Therefore, let me give you a little bit of a rundown what we have prepared for you. And you saw just this image on the screen, and it is, let's say, the first image from the surface from the Shiva instrument, but it's only part of a 6-image collection, a panorama that Shiva can take. So you saw 2, and we're going to present the other 4 images in a few seconds. Another question that is extremely important is, where in the end did we end up with Philae? Stefan already said yesterday, at least we flew again, twice. He said we touched. Let's see whether that's true. And from that, it is important to understand where finally Philae sits at the moment, what the attitude is, what it can do in terms of science, because there's a lot of science still to be done. And these are the 3 questions we're going to answer in the next hour. So the lineup is Jean-Pierre Biebring. Jean-Pierre is the lead scientist on Philae, and he is also the PI on Shiva that took these stunning images. Jean-Pierre, you can already come. Huh? Then we will have Stefan Ulamec. He is the DLR Philae project manager, and he will tell us where Philae has landed, how it has landed, in which condition it is. Then we will go again to the Lander Control Center at DLR in Cologne to hear some news from Koen Gertz. He is the Philae operations manager there. And then we would like to try to reconstruct the descent, because it was really an amazing one, I can tell you. And Holger Sirks, the Osiris PI, has a sequence of images that will show us how that went in the end. And then we will get an update from the MCR here in ESOC, latest status on Rosetta. And that will come from Ignacio Tanco, the Deputy Spacecraft Operations Manager. Andrea Akamatsu will join us with more emotions, like we saw before. And also with an update on the spacecraft itself, and a little bit looking into the future. And finally, Fred Jansen, the Rosetta Mission Manager, will give us a good understanding of what is going on in the future. And with this, I would like to hand over to Jean-Pierre and allow him to give us another stunning set of images.
Thank you very much, Marcus. Thank you, all of you, to be here again. And maybe we'll meet together also tomorrow, who knows. Well, you know, exploration is that sort of venture that happens only once in one's life. And when you're in a process, you don't have necessarily the prospect to see where we are, like revolution. I think we're really in a core revolution with what we are doing here. As we said yesterday, yes, we wanted to land, we landed, then we rebounced. Even more than what we thought yesterday, actually. From the science data we collected up to yesterday evening, we understood that we had 3 flops like that. And finally, we rebounced 2 times and finally stopped in a place where we are not entirely located, but we sort of get close to the place where we are, where we think we are. which is not very close to the one we wanted to, but not very far away. We thought that, you know, when we discussed the landing site, we had to choose one, and we finally decided to explore several. That's what we did with this mission. We explored several sites. Around the B sites, we showed the G site and the J site, and now we are sort of on the other side of the B site, probably. And that's a result of the brilliant science reduction of several instruments, in particular the concert instrument, that after an entire 10 hours of integration has been able to do two things important. One is to probably locate us on the Comet, I'm sorry. I'm just tired because in 2 nights without sleeping, it's a little tiring. And the other thing Concert has been doing, which is absolutely brilliant also, they have completed their first crossover the entire planet, the tomography, and so probably in the coming hours we'll have an idea whether this structure exists in both lobes, in one lobe. We will know that rapidly, I guess. So it's really a very good success on that side. Many of the other instruments are already acquired what they wanted to. The ROMAP instrument have acquired the magnetic field around, and they will soon also release some important data on whether or not this material was magnetized or not. And we have this Hollis imaging that could make some images just below the place where we landed a few hours ago, actually this morning. And they have already shown that we are very close by places, a few tenths of centimeters, for which they have the resolution. So yes, a lot of science is getting covered now. And I will focus now on something which, at least to me, is really moving. It's not only the first image that Shiva has acquired, the first ever acquired image from a comet. So sure, you saw already what we put on the website this morning, and I just want to demonstrate to you the sort of process in which we were this morning. It was both very exciting when we knew that the first images were to come from the lander, because it demonstrated first that we were alive, which is not trivial, that we have stopped navigating over this comet, and then everything was fine because we could really transmit data from the lander to the orbiter, and then of course from the orbiter to the Earth. It takes some time. We arrived early this morning, and these are the set of images. So please consider that it's really work under progress, as we say normally in English, I guess, and that will be processed in the coming hours. So they're not really good quality yet, but for those who are really interested, that will be, of course, distributed soon. You will have some of them already in the afternoon. So this is what we call the camera 1, when we were very happy to see, I don't have, okay, on the bottom side here, one of the feet, you know that we have 3 feet on the Philae, that's one of the feet. And what you can see, we didn't know whether we would see something on the back side, whether it was the open sky or something else. And when you just stretch the dynamics, you see something which we love really, which is like a huge cliff ahead of us. Of course, when we stretch that without any other processing, we overexpose the foot on the bottom side here. But you see, we are just in the shadow of a cliff, and that's, as you will understand soon, it's part of the problem in which we are. Of course, we wanted to land independently where we would like to be, but of course, to be the more illuminated would be the best, and we are not really well illuminated. So you see a cliff here that really are delighted. It also gives you, but you are not necessarily happy with that, a very good quality of the imaging, because we go to something almost black, which you can really see some details, up to saturation. And when you do something like that, you have just a first process image of that without the feed, just to remove what has been overexposed here. So we are exactly below that sort of a cliff. Do not ask me what the distance is, because we don't know yet the distance. It's probably a matter of meters, but how many of them, we don't know. But we are very close by, because of that, we are sort of in a shadow permanently. And that's part of the problem. That's a second images, because we turn around, you know, the beauty of our imaging, that we have images all around that. So even without turning the system, we know exactly what it looks like all around. So we have a second camera taking this view that we like for many reasons. The circle that you see are just reflection of the sun. So we are in the open space, and the sun is just reflecting on the baffle of the camera. And what you see down there, the straight line there, is one of the concert antenna that has been used during the night, again, to make the first ever tomography of a small body. And essentially, this is it. All the rest are stars in the field of view, because we have stars in the sky. Next, we go there, and we were really astonished when we saw that this morning. It was a good time to open the champagne again, because you saw both something that man built, really, a lander, because you see the foot there, and something that nature built 4.6 billion years ago, which is a comet essentially preserved as it was at that time, containing all the mystery that we are trying to look at. So this is really something that we have no idea what is around, whether or not what is black is just in the shadow or in the open sky. And then we have these next images, the camera number 4, which is really astonishing because we thought we would land in sort of a highly powdered material, and that would have been a little complex to understand how we could rebound 2 times and to make 3 travels in open space for hours, actually. We travel in open space, which is also a first premiere. I think never someone did that, 2 hours in the open sphere around a small body. But when you look at that, and we'll do that in more details, of course, in the coming hours, you have a lot of, it's like a rock. It's not a powder, it's a rock, and that explains that this material is like a trampoline. It goes there and ejects you immediately afterwards. Then we go to this image. This is essentially the only processed image that we did this morning that has been released in even high quality. We'll go there to low quality rapidly, so take it rapidly if you want to have the high quality one, because it's very high quality. All the science we can do from high resolution imaging is there. Then the next are the images that we had to stretch a lot if we want to see details, really, because they are almost below, in the shadow of ourselves. And so there is very, very little light here. We will redo, actually, the panorama sometime in the evening with higher exposure time, just to try to increase the possibility we have to see detail there. But these and the next one are things that we can, and actually we have a stereoscopic view of this one, and possibly in the next hours or days you will see an anaglyph of this one. It's the how do you say paroi in English? I don't know the word there. Well, the wall, yeah, the wall, which is about a meter away of the lander, and we have good resolution of that. So when you put all that together, this is a sort of panorama. If you were to sit on the lander, turning around, that's essentially what you would see. And to give you an idea of the way we think we are located, so open sky is upwards, and that's where we would be now. And so we consider that that gives you an idea of the travel we had and the way we landed finally. We're almost vertical, 1 foot probably in the open air, open space, I'm sorry, there is no air around, open space, 2 feet still on the surface, but you can imagine the sort of gentle maneuver that we are supposed to do now to maintain the strategy and the position of our lander there. So essentially we already accepted ideas on what to do next, but we will do that in the next hours and possibly days. We will try to optimize the illumination because we still have possibility to maneuver things that might, by reaction, modify the orientation of our lander. So possibly for the next panorama, when we'll show that up, you will see that we are no longer in that orientation because we might try to better orientate the solar panels vis-à-vis the sun. And meanwhile, we'll have operated part of the other instruments that require to be operated, which are the thermal sensors on MUPUS, the APX to measure the elemental composition, and hopefully the drill that will finally bring samples to be analyzed by the mass spectrometers. I think I will finish there. Thank you.
So, ladies and gentlemen, I know you would want to ask a question afterwards. Please, thank you. Thanks a lot, Jean-Pierre, Shiva, Pi, and now Stefan Ulamec. Okay, Stefan Ulamec. Good. Finally, after 2 years, not bad. Okay, Stefan, how did we get there where we are?
Yeah, we have a better understanding now how we got there. We still do not really know where. So yesterday I said we probably landed twice. It's already been announced. We landed 3 times, so there is an inflation of landing somehow. The first rebounds, and this we analyzed now in a bit more detail by using the data of the time of the jump, which we know by looking basically into ROMAP data from the magnetic field. We have a clear signal when we touched ground and when we stopped there, also from the thermal mapper. as well as from the data we have from the landing gear itself, which the first time was pushed in due to the first impact. So now we know the first jump was, as announced also yesterday, about 2 hours, 1 hour and 50. We assume we came in with about 1 meter per second, and then we rebounded with about 38 centimeter per second. At a 2 hours jump, probably up to 1 kilometer, probably also around 1 kilometer distance, and this makes it difficult to find out where we are now. We know very well where we touched down the first time. It was a huge leap. And then we had another very small jump of about 3 centimeter per second for a few minutes, for 7 minutes. And now we are in the configuration, as you've seen in the images here, and I cannot really tell you much more than what you interpret yourself by looking at these wonderful images of Shiva and think about what could this actually mean, what could this mean where we are landed. Now I have one picture, I hope it has been uploaded, which shows you the result of this first analysis by CONSERT, the radar instrument, and I don't know if Mark has uploaded it. Just a second, okay. Well, radar tomographer, the CONSERT instrument, was designed to scan through the cometary nucleus and get information on the internal structure. Now, this information, and this measurement was done tonight, was also used for reconstructing where we are by assuming a certain dielectric property of the comet. And you still don't see this image. Coming, good, so I keep talking. Was used to give us an estimate where we probably are sitting. And the interesting thing is we did a lengthy landing site selection process. We were not sure about landing site J or I or B. Maybe we landed on all 3 of them. Because I keep talking. It's coming from the comet. Yeah, it's 28 minutes. I have to keep talking for 28 minutes. We made, as I said, quite a leap, about 1 kilometer. Well, in the meantime, while we are waiting for this, some other status report, because yesterday evening it was, of course, not clear whether we would get signal from the lander again. And, of course, you all know this right now because we've presented here the nice images. But very accurately, at the time we hoped to get signal, we received radio link from the lander again this morning. It started again with a few interruptions, and then we had for several hours a perfect link until we lost signal again this afternoon because the orbiter is below the horizon again. So we are currently in a mode where some of the instruments are operating again, which do not need mechanical activations. So this is SESAM is running, ROMAP is running again. From MUPUS, the thermal mapper is running again. And this evening, hopefully around 7:22 UTC, we should re-establish link, and then we will upload the newest science sequence, the newest sequence we want to operate on the Comet. This is currently iterated and discussed. Since we do not really know how we are landed, since we are not anchored, but somehow just with the weight of the lander, we need to be very careful about activating mechanisms, but there is some tendency to deploy MUPUS. This is the PEN instrument and also the APX in the coming AOS. AOS means the time when we have the link. So the 28 minutes to get the picture are almost over. There it is, yes. Okay. So here you see, you saw the other picture. This is the big crater on the head of the comet. This is the nominal landing site, and we hit this quite accurately within less than 100 meters from the really predicted point. This is known. And then we did this huge jump, something like this. And the CONSERT data imply that, and it's a bit depending on what dielectric properties you assume, somewhere in this area. So we are somewhere in this area, and just to remind you, this was landing site B within the crater. Here was landing site J. So I was joking, we're somehow jumping from one pre-selected landing site to the other one. But we are somewhere here, and it could also well be that we are somewhere here in the rim of this crater, which maybe could explain this kind of bizarre or not so obvious orientation you've seen. That's what I wanted to tell you today. Thank you.
Thank you, Stefan. And now we are going straight into the Lander Control Center in Cologne, and I hope there is Kuhn Gertz ready for us to answer some questions. And that is not Kuhn Gertz, but this is Stefano Mottola. Stefano. Now the microphone is passed over to Kuhn Gertz. Yes, here is Kuhn. Hello, Kuhn. I hope you can hear us good. Kuhn, I mean, you had a really nerve-wracking night behind you. After landing, it seemed that really the work started to, get into a field where everything was unexpected. Can you give us a little bit of an overview what happened through the night on your end, and also a status of Philae? Thanks a lot.
Yes, so after our first touchdown signal yesterday here at the LCC, we saw immediately that something was not nominal, because our system data was indicating that the lander was still moving. And this can only indicate that we're not standing on the comet's surface in a solid way. So we were monitoring this because fortunately the communication link between Rosetta and Philae remained intact also after the touchdown. And we continuously saw that the lander kept rotating. We observed this for about 2 hours when we saw a change in this, and we saw that the rotation stopped. For us, this was a very good signal, because the rotation could only stop by touching the comet again. So for us, this was a clear indication that we're at the comet. In these 2 hours, we were talking with all the scientific instruments that were measuring during these 2 hours in order to understand what was actually happening with the lander, in what kind of way we were rotating. And they could quite quickly confirm that we were in a position that was not dramatically different from what we would want to be. Of course, in 2 hours, we could not know where we have landed, but because of the communication between Philae and Rosetta, we kept receiving data, so this was all a positive sign. About 30 minutes after, let's say, the final touchdown, we lost the communication link with Rosetta, but the experts that were here with us looking into the communication could tell us that this was a normal end of the communication. So Philae was disappearing at the end of the horizon, and this gave us good indications that around a comet rotation later we would get a communication link back, and this is what happened this morning. So we were very eager to get the communication link back this morning, and we started to receive the scientific data that was generated overnight. So we have the concert sounding science data coming in. We have a Rollers-Cook image that Stefano will probably talk about after me. So the science measurements were conducted normally. We can say that the lander, from a system point of view, is operating normally. What we need to understand now is, what does this position mean for us? You saw in the presentation of Jean-Pierre earlier that we're not standing, let's say, parallel to the surface. So what we're doing now is we're seeing how we can modify the planned nominal operations to cope with this non-nominal position that we're in. And we're at the moment, that's why I came a bit late, we are preparing the commands to be uplinked in the next few hours so that we can start with the next scientific measurements.
The point is a little bit also, before we go to Stefano Mottola to see some other images of Rollis, the point is a little bit, if you are in a position where there is, let's say, not as much light as we would like to have to be there, what does this mean for the next days or for the next weeks?
Of course, the lander is relying on solar energy to operate over an extended period of time. We have a primary and a secondary battery that we're using now. We see that we get less solar power than we planned for at the nominal landing site. We're receiving about 1.5 hours of sunlight with respect to the 6 or 7 that we were aiming for. This, of course, has an impact on our energy budget and our capabilities to conduct science for an extended period of time afterwards. We are calculating now what this means for the near future. So at the moment I cannot say much, but unfortunately this is not a situation that we were hoping for.
And again, congratulations for the fabulous job you've been doing so far. I mean, everybody is just thrilled by the images thanks to your work that have been coming down. Of course, also thanks to the work of Jean-Pierre. I mean, great job. Thanks a lot. And now we are coming to the other topic. I said, yes, nice images from the surface, but we need to understand how we got there. So now we are talking about this descent. And yesterday, during the descent, Rollis already took some images. And that's how Stefano Mottola comes in. So we are going back in a few seconds to the LCC, the Lander Control Center in Cologne. And Stefano is going to present other Rollis images taken during the descent that basically show us how we got closer and closer and closer before we basically bumped off and tried to land on 3 landing sites. Stefano, are you already there to tell us something? There he is. Stefano, Rollis is a brilliant instrument, nice optics, and when it's going down, it gives us a lot of detailed, more and more highly resolved images when we go down. You have been taking them, and now you are presenting those to us. It was a lot of work during the night, so that's also why you've been a little bit late, and we bring you in now like this into the program. Can you explain what you saw, what you found out through your images, and explain a little bit what image you took?
Yes, this is correct. We have been very busy during the night collecting the images that have been acquired during the descent and after the descent, and calibrating them and analyzing them. And we're really amazed by the quality of the images. Yesterday we have been showing one image that was taken from 3-kilometer distance from the Comet that showed the context. And today I'm showing an image that has been taken 40 seconds before touchdown, or the first touchdown. And it has a resolution of 4 centimeters per pixel. We have a side which is 4 meters here. So we see that the comet surface is covered by dust and debris and blocks from sizes from millimeters to meters. And to understand the distribution of these particles, it is very important. We have seen from the orbiter, for example, that there are a lot of millimeter to decimeter size particles that are flying around. Some of them get into orbit. So now we wanted to know where those particles come from the surface. And now we have this missing link, so we can exactly trace down what on the surface this object come from. If you can put the image in again, we can see also that we see that there are some big blocks. One block on the top right corner of the image is about 5 meters in size. We can see that it is partly covered by dust. So we do see here, for example, that there are active processes at work. So we know that dust is mobilized on the surface, for example. It is not clear yet whether, for example, this rock was covered subsequently by dust, or whether it is slowly being exposed as dust is lifted by sublimation of the gas. So this is something we need to understand by studying the images better. Anyway, these images provide us with a wealth of information that will keep us busy for quite some time now to understand.
Ladies and gentlemen, Stefano Mottola, he is the PI of the Rollis instrument, and of course he has still a lot of work behind and before of him, and then he will come back with scientific results. And as life is life, and we wanted to get live into the MCR here, and they are busy with operations. We do it now, and then we come to Holger Zirks and we talk further about the descent. But now I would like to talk to Ignacio Tanco, and he is the Deputy Spacecraft Operations Manager, to let us know more about the current status of Rosetta. Ignacio.
Hi.
Can go ahead and let us know what is the current status of Rosetta, Ignacio.
Okay, so, well, after the last 2 days, which have been a wild ride, a roller coaster, one would say, the mood here in the MCR is jubilant, and we are all very, very happy at how things are going. So the situation with the orbiter is perfect. Rosetta is performing flawlessly. And after this morning's pass overflight of the lander and the acquisition of the signal, we are very relieved now to be carrying out the operations. And of course, we are continuing with the preparations for the next pass this afternoon. And of course, the maintenance of the relay trajectory of the orbiter, which will require a correction maneuver sometime in the early morning tomorrow.
Thanks a lot, Ignacio. I have one thing I would like to, get your comment on, because, delivering a lander is kind of, you need to aim, okay? And we had already a landing site that is 500 meters radius, 1,000 in diameter. So that's a huge one. And what I understood, it was almost in the center. Is this something you can confirm and maybe share a little bit, whether this is something, that is, kind of professional pride in the profession?
Okay, well, certainly it's an enormous amount of pride to be so successful or involved in an operation that has been so successful. I must say that, of course, I cannot, or even us within the team, none of us can individually claim any responsibility more than, a tiny amount of it. There has been a very distributed and there has been a lot of people involved in this operation. The responsibility, of course, goes to all the people that contributed. I can think especially of the colleagues of Flight Dynamics, which have done an absolutely amazing job, and the mission and the success of the mission to a great extent rests on their shoulders. So. But yeah, certainly it's an enormous professional gratification to have achieved this level of success.
Thanks a lot, Ignacio. Ladies and gentlemen, this was Ignacio Tanco, Deputy Spacecraft Operations Manager. I mean, the next time what we could try is... The next time what we could try is not only land in the middle of the first landing site, but when we jump, we could also do it on the second and the third. But, that's for the future. And now we are talking about the descent and the brilliant images of Osiris and Holger Zirks.
Okay. Let me take pride of talking after mission operations and flight dynamics, and give all credits to flight dynamics. These guys are the heroes of this mission. They are so great, so let's give them an extra applause. This is unbelievable. So Paolo mentioned this. It's accuracy. I mean, it's unbelievable that they brought us there. Our role on the orbiter is very limited. So we provide contacts, and so nothing more, nothing less, but nothing more. So it's just contacts supporting the whole mission and the lander that do such a great job. I want to take you back a little in time. So before landing, actually taking you from where we left you yesterday, with this wonderful close-up from about 2,000, 2,500 meters. We still have to do some math. So the first image we could take after the retreat of the orbiter and the rotation of the body. And overnight we got a set of images every hour, a set of image down. And so it went ever further. So with the next one, you will see our wonderful lander moved further and further away. Bye-bye. Here you go. So it's one image an hour. So you'll see it's two things. It's the configuration, and I was surprised to see it in this configuration because it's already prepared as a CAD for landing. So it's the whole landing gear is laid out for the moment of touchdown. I was expecting it in a different configuration. It's so wonderful to see. Plus, you also see within an hour, it does a rotation, and it's allowed to rotate by a degree, a minute, a second. It's not my business, so you know better. So it's rotating it on its way down. So that's what came down overnight. This morning, we got even better images down that were in the pipeline for a later transmission. So I have another one to show, which is a first shot, but with an optimized exposure time. And oh wait, sorry, I have to go one step back. So this is a shoot with a wide-angle camera. So we are there. This little guy is our lander with the wide angle, about 65 minutes or so before contact. So it's wonderful to see them both, the lander and the landing site, the head of the nucleus. So sorry, I will come back now to the wonderful shot at best exposure, the closest it can be to the orbiter, and it's this one. So that's for me the best image I could ever think of. You even see the structure of the solar arrays very nicely, the antennas. So you see the full structure of this little guy, first time in flight and on its way down. That's actually what we can contribute. I would have wished to show you where we landed, but cannot. So we are not there yet, so don't expect I could spot you. This is where we are. But I can show you from the context provided by the Rollis camera where the first touchdown was. So let's see if this works. So this is the well-known head of the smaller lobe. You reckon the big depression, and so here at the red cross, this is the landing spot, and I show you why we think this is true. So this is an image taken from 50 kilometers pre-landing, just context. This is a zoom in an image taken about a week ago, so there is no lander in there. So a week ago, this is the spot we landed on, and we couldn't have had better luck. Look at this, it's flat like hell, so really great. And we know this from the Rollis image Stefano Mottola just showed. So you will see it here, clong, clong, clong. This is the center, clong, clong, clong. Here is the lander touchdown number 1. So we would have wished it stayed there, but we know it didn't. And we'll have to go through more data now to find the lander. So I will show you an unsatisfying image to me, and I think to all those who run cameras, which is an overexposed image. So we look down with a mosaic around landing. This is the lower right is taken some 8 minutes pre-landing, so the lander would be, if in there, still a few hundred meters above ground. The rest is the raster taken post-landing. The cross is where we know the first touchdown was, but we have a hard time to find the lander. We are waiting now eagerly to get the next sequence down, which has a lower exposure time, so we increase the contrast as usual. And we'll...
A little bit of a wrap-up, because what a mission, Andrea.
So I was hoping to stay there because I'm a bit tired, sorry. I'm not going to present slides, I have only a couple of words. I want to say first that we are all tired, but as Ignacio already said, there was a huge effort of a huge team. I think it's worth mentioning a couple of features of these teams, not features, but masterpieces of this team. It has been mentioned several times what the colleagues of Flight Dynamics have done, and I'm not going to repeat what they've done, but I want to point them out. And they're sitting there, and for me, they are the best in the world. Nobody else can have done what you have done yesterday. So you are the best. So they deserve the image of the day, in my opinion. The other one is Ignacio is the Deputy Spacecraft Operation Manager. I've been the one for several years after Paolo, that I don't see him anymore. But okay, we have a long tradition there. And the current Spacecraft Operation Manager is Sylvain Lodiot. Sylvain has prepared all what we have done yesterday, has coordinated all these activities. And he was so professional that he worked out all the night. And to be fit for last night, he was not here when we landed. And I'm sorry if I go a bit emotional, but to give up and give up something like this, you have to be very, very professional. And my personal thank goes to Sylvain, because I'm not sure I would have done something like this. What we have ahead of us is a fantastic mission. We have flown this mission not for operation, which is very fun to do it, it's very rewarding, but we have flown it for science. And the scientists seem to be enthusiastic now. There's more scientists that want to do much more, and we are preparing for it. The mission is not over. For us, it continues, as Ignacio said. We are preparing for the coming days, the coming weeks, the coming months, and maybe a couple of years more. So I wish everybody that in a couple of years, maybe, we are still here talking about this fantastic mission, and this fantastic team, and this fantastic Comet, and for more fantastic science. So thanks a lot.
Thanks a lot, Andrea.
Okay, after Sylvain, I have to now hope I make it without tears to the end of my presentation. I just want to say a few words. It has been an absolutely magnificent 2 days. I never thought when I got this job a year and a half ago that this would be the impact it has on people, that you really get to do this and land on a comet. Of course, when you're successful, like the lander now is, taking measurements on the surface, you'd like to continue this as long as possible. Reality tells us, as Koen already indicated, there is a limited amount of battery power. The solar arrays are not really illuminated, so we don't know how long we will operate. That always was known. This was Philae, as defined. So we have a wonderful mission. Of course, you want it to continue as long as you want. But Rosetta continues for another 20 months at the Comet in what I call the Rosetta Adventure. And I'd like to thank everybody over all of Europe, US, anywhere, who works on Rosetta, who really the last years have worked their off to really get this mission going. Thank you.
As promised, question and answer session. Please come to the stage. Stefan, Holger, Jean-Pierre. And also we can switch back to LCC. So we do a first round here on stage with the gentleman here. And then we go back to LCC to talk again to Koen and to Stefano. Now, where are the microphones? Or am I the microphone boy again? Please state your name, affiliation, and give back the microphone.
Hi, Eric Ham with Science Magazine. I was hoping to ask a question, I guess maybe for Jean-Pierre or maybe Holger, a geology question. We're getting slightly conflicting information. We were told upon landing that we landed in very soft stuff. And, you know, we see from the Rollers picture, you know, this very soft stuff with mobilized dust right in the middle of Site J. But then we see these Chiva pictures maybe near a cliff wall and things that really do look like rocks. So I was hoping one of you could explain what these materials are and how they can be explained by being made by Comet processes. Thanks.
Okay, what you are asking for is to try to be ahead, 1 year ahead of us, because we make this mission essentially to answer the question you're asking now. So it's normal that we don't have the answers, and probably the answer would demonstrate that the question is not really well formulated. When you say a cliff, for example, it has some resonance in our head that a cliff is terrestrial sort of cliff analog. We don't think that we're that sort of cliff, because the material is very low density anywhere. The density is less than 0.5 globally. So the idea of having a very porous material at the very top came from that, to the idea that there is no reason to believe that the crust is really a strong crust, as we thought in the past, on a very low density material there. So that's why we thought that finally, with the first images we had, plus the Cosima measurement showing that the floating grains were very fluffy, very porous, that we might have that when we landed. We are not saying that actually it's not the case. It might still be the case. You might still have some really fluffy power, out of which you are, after rebouncing again, the ejection velocity is very low there. So I would not be more accurate than what we have found does not demonstrate that we don't have a crust. It does not demonstrate that it's a crust. Are you satisfied?
Thank you,
so
Jean-Pierre.
I'm really happy with you not satisfied.
Let me just add one word. So I would follow you on that thought that the rebounds of the lander is an indication of a higher strength material. That was a surprise to us. So with this picture of dust falling back to the surface, building high porosity layers, I would think we failed to explain the rebounds. So, but we have seen the variety of surfaces there, this snow-filled soft stuff, and we have seen this rocky-like but no rock stuff, which is perhaps a higher strength material. We also see stuff shining through a dust layer where the dust is wiped away or following the gravity field and exposing a higher strength material. And this is something that we could consider be the reason for the rebound. So bounce in there, find a higher strength material, and then get going for the next landing.
Thank you. David Schuckman, BBC News. You've ended up in a very awkward spot. Is it possible to get out of it?
We just need another jump. Well, in this context, I should maybe mention a person who hasn't been mentioned very often today, but should be, and this is Helmut Rosenbauer, who is the father of the Philae, the idea, Max Planck director in the whole development phase. And he is also somehow the father of this landing gear. And he put in a lot of ideas and thought. And when we designed the lander, indeed, it was his plan to make the lander in a way it could hop by extending the landing gear again and make a hop somehow like we did it without really wanting to do this right now. So we could, in principle, operate this landing gear. But in the position we are now, which is very unclear, with one leg maybe somewhere in the, not the air, in the vacuum, a position we do not know, we wouldn't dare to operate this right now before we know where we are and what would an activation of this landing gear really mean. So I'm not so sure we would have enough time, given the limited power we generate with the solar generator, to do this analysis, really to do a dedicated jump out of the hole where we might be or away from this wall. So there is some principal possibility, but it would be very, very difficult.
Okay. Other questions? Oh, that's far away. While I'm walking with the next one, we'll go to LCC. So if you have any questions to ask to either Kuhn-Gertz or Stefano Mottola, then you will have the opportunity after this question, of course, as well as the answer.
Do you think, Andreas Hieke from Hessischen Rundfunk, do you think the construction of Philae should have been different?
If we had known the comet, we may have thought of something else. Still, we put a lot of thought of possible scenarios and possible surfaces. And as much as we know right now of this comet, I don't think we would have completely differently designed it. And the fact that in principle the landing worked, although with the rebouncing which was not foreseen, also shows the high redundancy we put into this design, and some aspects like the cold case system or the harpoons did not work. But the landing gear worked very nicely. This redundancy in concepts in order to cope with a wide variety of possible parameters, how this comet may look like, is something I will also implement in the next comet lander.
Thanks a lot, Stefan. Before we come to another one from here, there's a question coming from LCC. So let's see whether we can establish. Yeah.
Hello, it's Chris Lintott from BBC Sky at Night. I'm interested in what the instruments on board knew while they were bouncing around. Did they think they were on the surface and execute the science package, or would they have gone into some safe mode or reacted to the fact that the Philae was moving? The Philae.
The touchdown signal was generated at the first touchdown, and this switched the lander from the mode of descent into the mode of what to operate after touchdown. So after this touchdown signal, the instruments thought, as you want to say, that they were on the ground, and the sequence started as it would have started on ground. But these measurements could then, of course, be used to interpret and to learn that we were not on ground, but actually jumping. Like I mentioned, the data from the magnetometer, which clearly indicated this in the coming back, and also the infrared monitor, quite clearly, as we understand it right now, showed us when we were not properly standing on the surface, but doing something strange, because they had the comet in the field of view and then not, and then they had it, so that they measured this. And in principle, after this touchdown, our first scientific sequence with the first block started as if we would have been on the surface, safely anchored.
Thank you very much, Stefan. There's another question from LCC. Can you please let us know your name, affiliation, and of course the question?
Leo Enright from Irish Television. I wondered if you could perhaps give us a clear indication of your expectations for each of the experiments. I got the impression from what you were saying that you were confident that APX, for instance, might work, but very much less confident about the drill. So could you work your way through the different instruments and tell us which ones you think are most likely to be deployable in this attitude, and which ones you no longer have any confidence? For instance, I presume the harpoon and the thermometers and whatever on the harpoon are no longer viable as instruments.
I don't want to work through the instruments one by one right now, and I certainly will not judge the scientific results we are receiving and we have received already. What is true is that we are very hesitant, or at least we have to be very careful in order to do any kind of mechanical actuation. So we are also hesitant in the next hours or day to activate the drill, because drilling without being anchored and without knowing how you are on this surface is dangerous. We may just tip over our lander. Each of the instruments, if we run this block 6, which also includes APX, will have received some data. As said, the drill is something problematic. We have to look very carefully into it before activating it. And also people keep asking me whether we would do a second attempt in firing the harpoons. Same applies here. I'm hesitant in firing the harpoons before we really know the situation, how we are there, because obviously the harpoons, if they would not perfectly anchor for whatever reason, because they are firing in the wrong direction or so into a hole, or the material is too soft or too hard, would put some momentum on the lander, which again could just make us another jump and push us away from the surface. So these activations will not happen in the next hours, for sure.
Thank you, Stefan. Jean-Pierre might have something to add. Thanks.
Yeah, well, We are on the Comet to operate as much instrument as possible. So as has been said, of course, we've got to trade off the risk we take doing something and the goal of the mission here. So we'll do priority, essentially, just to be careful there and to go to the less risky to the more risky. Take into consideration the importance of the science also. The question of drilling and analyzing the samples is a key question because, of course, it's part of maybe the core of the reason why we are there is really to analyze all the samples by all means. And we have a huge variety of good instruments on board that have to be practiced also, using in particular the drill. So my opinion is that as soon as we can, and that might be maybe the end of next night or tomorrow afternoon, when we have the possibility to test that, maybe in two-step things, the possibility to acquire samples and to feed these samples into both Ptolemy, the British instrument, and COSAC, the German instrument, with French contribution, actually. To know the composition of the organics in particular, the isotopic composition is so critical that we might do that, so too. And prior to the potential end of our system, if we cannot augment the elimination there. So the proper approach, I think, is to go step by step in the coming hours, but we have some flexibility on board. And it means that first we have to optimize as much as possible, and that's been already brought into question. Do we have to can we modify the orientation of the things, not only see hope to another place, but at least to optimize things? And the answer might be yes, because each time there is such a low gravity that each time you manipulate something, you have a reaction. And if we are clever enough, this reaction can optimize, in particular, the amount of sun we have on the solar panels. So doing that first, to try to optimize the possibility to survive as long as possible. Then, of course, we'll take into consideration the possibility to actuate all instruments with some sort of priority, which is driven also by science. And, of course, the drill and the instrument that goes with are part of that. So what is to be decided is probably that for the next opportunity, which is tonight, we will not drill. We will go to the thing that will both couple more science, like APX, for example, and the thermal measurements of the potential gradients in the soil that MUPUS will provide next night. And that also include a movement, an ejection of system that might optimize the possibility tomorrow to go to the drill rapidly enough for the drill and the according instrument to be operational. So I wouldn't like to give the idea that we have already decided that part of the instrument are already out of the scope. They are really more than in our scopes.
Thank you very much, Jean-Pierre. You see, it's a really complex puzzle that our scientists and engineers have to solve. And there is more to come. And if there is more to come, then tomorrow we will do also a Google Hangout at 1400. I will come back to that later. But now we're coming to the next question.
Thank you. Ivan Semenek with the Globe and Mail newspaper in Canada. For Stéphane Oulimetz, what is the thinking today about why the harpoons did not fire? And given what's known now about that first touchdown point?
We don't really know yet. What we know is the harpoon mechanism has triggered. I mean, the touchdown signal was acknowledged. The rewind spools also started. That's what we saw in these very first moments when we said touchdown and the harpoons are activated. Yes, the coil was activated, but the harpoons actually were not fired. We are still investigating what was the reason behind.
Had they fired, do you think they would have prevented that first bounce?
If they had fired and anchored, of course, yeah.
Thank you, Stefan.
There is an end.
Okay. Yes. Okay. If you look at that gentleman, they all have been working through the night, more or less, so they are tired. Some of them need to get back to prepare the next stuff. I would like to start slowly to wrap this up. But of course, let's say another 3 questions from here, and maybe if there's another one in LCC, we will take them. Ladies first.
Emily Lakdawala from the Planetary Society. There were some reports circulating this morning that the solar panels had actually suffered some damage in the landing. I'm wondering if that or any other part of the spacecraft suffered any damage in the landing or not.
Was a wild guess why we didn't get sun on all of the solar panels. I don't think so. I think the solar panels not generating power are simply in the shadow, but not damaged.
Thank you.
No indication for damage.
And Jonathan Amos from BBC. Jean-Pierre, how late, or Stefan, how late in the 60-hour window can you do some drilling, get some samples, and get some data off? How late in that window can you do that operation? Because you want to do it at the end rather than risk the other operations.
Well, this is really a question how long our primary battery will last. So for the next AOS, for the next day, we're safe. For the day after next, it will become critical because we get very little power at the moment from the solar generator.
Okay. Oh, there is still one hand. Ooh, that's also an interesting position. Stay where you are.
Rainer Riemann from Raumfahrt Konkret. Will your position, weather position, and will it improve the solar power during the change of season? Because the comet moves and...
Well, okay. Even if we think the mission ends because the first science sequence may end and the battery are low, the lander is not necessarily dead. I mean, it will go into kind of a hibernation mode when it chills down, and it's programmed in a way that whenever it gets sun, it will first, this power generated from the sun will be used to warm up the compartment, warm up the batteries, and then start charging the batteries. So if even in months or so the solar situation would change completely, we could still wake up. So most probably the lander can somehow survive in a very inactive mode. But this is at the moment really, I mean, we were very, very lucky yesterday, so much luck to wake up in a few months from now. I wouldn't dare to estimate this now.
If I may jump off the question. It's normal, that's essentially your job to put the emphasis on the failure modes. I mean, if we had a lot of failure to present to you, you would be very happy with. I would like to say that at that point, really, it's true that the question of risk and failures are fundamental. I mean, we are always thinking of that. But what's really impressive is not really the degree of failure that we encountered, but the degree of success we had here, and the possibility we have to go to the end of what we wanted to, which is really to analyze this material there. So at this point, I think the message to go home is certainly not to say, well, they are here or there, but they might or should have been elsewhere. It's amazing where we are. We landed. We analyzed a lot of things already in 20 hours. It's amazing what we have been doing, or what we'll be doing by the end of this day. Tomorrow it will be only another 10 or 15 hours during 3 more instruments will be on. It's really tremendous. Of course, we'll do our best to make even more than what we could. We are really at the limit of what humankind could do 20 years ago and still capable of doing now. But please do not put the emphasis on the failure of the system. It's gorgeous where we are. Thank you.
Okay. Thank you very much. Now, that was, as I said, that was the last question. But I have one important thing still to tell you. This mission is very much about images. And in order to get all these images, somebody had to detect the comet. And we have with us Churyumov. And therefore, I would like him to join the stage, that you can take an image of those people who made the mission happen, but also of the man who detected the comet.
Happy that landing event was successful, and I would like to congratulate all team will made this successful landing. Glory to even to all creator of all program Comet Rosetta mission, and all European country member of European Space Agency, they made the miracle possible. Glory! Спасибо вам большое. Спасибо. Спасибо.
This will really wrap it up because some of those guys need to get back to work. But final, last famous words, already mentioned all the time. Tomorrow is another day for Philae. 2015 is another year for Rosetta because the Comet will change dramatically. We are still around it. One of those firsts we achieved, rendezvousing a comet, and there will be a lot of images and even more science. I would like to thank you for your attention, for your curiosity, for being with us, for covering all this. And if you are trying to stay tuned, tomorrow at 1400 we are going to do a Google Hangout and that will be announced. Thank you very much for your patience and for your attention. Goodbye.
We definitely confirmed that the lander is on the surface, and I leave it to Stefan. I think it's up to him to judge how it's going now on the lander.
The landing gear has been moved inside, so we are sitting on the surface. Philae is talking to us, more data to come and to be analyzed right now.
We take an image that just arrived here, so it's really not processed, it's really as it is.
So we have the first images taken by the orbiter, by Osiris.
The lander may have lifted off again. We touched down, we're rebouncing. We still got radio link, we still get science data from there. So maybe today we didn't just land once, we even landed twice. Yesterday I said we probably landed twice. It's already been announced. We landed 3 times, so there is an inflation of landings.